Welcome to class 46 of CS. We'll discuss ARIMA model today. And here, these are the parameters P, D and Q. This is ARIMA and this is one form of non-stationarity. There is a integrated effect. Let's consider this example. Suppose the child is growing and this is the height. You can start measuring from 10 years and then 1 month here, 2 months here. You continue that way up to 15 years. Suppose this is 14, 11 divided by 12. And if you write this as 1 and 2 here, you count the time points. We're talking about 5 years. Okay. So starting from this one, maybe this will be 65 years. Okay. 60 months are there. So what we are doing here, we have to record the height. We are not interested in the weight now. That will come in multivariate. We are doing univariate. So we'll model only one such factor, that is height. So when a child is growing, we just record the heights. So we have data. This is a time series data in sequence of time. Let me write 3 here. So this data is available now. And we need to predict height when you will turn 60 or 61. I think 61. Yeah, probably, I'm not sure, but yeah, accept it, 61. Okay, is it? Let me confirm. If you start from 10 year 1 month. Okay, so if this is 1, I mean time 1, this is time 2, this is time 3. So when I write 3, I get 2 by 12, right? Odd number. 1, I am getting 2. So 11 means I will get an odd number here anyway. Okay, odd number. That means it should be 59. No, even means odd. So odd means it should be even. Yeah, 60, probably 60. Okay, so we have these data available now. Suppose we are here. Suppose we are here. Okay, we are standing here. That means up to this data, it's not looking good. We'll do this way. We are here. Okay, we are here. This is present. We are here today and we know the data available, we know already. We are here and we know the data till this point. Okay, we know the value here, we know the value here, we know the value here, we know the value here. So after knowing all this value, we are interested to know the child's height when he will turn 15 years. Okay, so this is what we want to know, when you will turn exactly 15. So it's 5 years, because we are including this one also, 10 and 15. This will be 61, and the data is a monthly data. Next month you will grow and we want to predict. Unfortunately, we will not be able to predict the height after another month, because there is an integrated effect. From time to time, if you see, the child is growing. If something is growing, the stock price is growing, or any such economic quantity is growing, we can't model directly using ARIMA model. It's not possible. Okay, we can't use one ARIMA model here. Let me write. This is not possible. ARIMA PQ is not possible because there is a clear indication ARIMA PQ. It's not that from 10 to 15 years there will be no growth. Even we are seeing there is a growth. Okay, if you see the sample data, we'll estimate correlation, mean, all those things later in time series 2. But now at least we know that it's growing. Seeing the sample, it's growing without calculating anything. We know that it's growing. Okay, so when I say the value at 10, I'm interested in the height. Okay, so whatever is the height, let me write a sample height. Okay, maybe I'll start with 130 centimeter, then 135, then 140.1, 144.9. okay, that way 1 2 3 4 all that you write. Then you need to predict using this data. This is 60 sample points. Sample in stochastic process means what? One at one point. Unlike a random variable, we get one sample at one point, that's all. This is a random variable. One is a random variable, x1. It could be anything, but now that this is a sample, this is a realization. Okay, so we got already 130. So x1 value is fixed now, 130. x2 is 135. That way we have the data. So since there is a clear indication that it's growing data, we can't apply ARIMA PQ or AR. You can't apply this. There is an integrated effect. As I already mentioned, there are different forms of non-stationarity, and we have to recognize here that ARIMA doesn't cover all forms of non-stationarity. We'll go to all those things, okay, later. If there is a seasonal pattern or something like that, we are talking about the data which is growing, okay, continuously growing, integrated effect. From time to time, something, there is add-on effect. Okay, there is an add-on effect from time to time. So then what you need to do is, you want to, that add-on effect we don't want. We have this data. Now suppose you need to subtract the first one from the second one, you get 5 here, and here also if it's not 5, it's 5.1, and here it's 4.8, maybe around 5 we can say. And if you subtract here 150, okay, 6 you get, but 3, this is 3, 144, 150, 12 minus 9, 3, so maybe it's 5.3. And here also 1 2 I've written, okay, 20 here, so 4 point, 4 point here from 12, okay, you make it this 4.9. Now if you difference once, then what will happen? This data, if you see this transform data, they are stationary. Okay, they are stationary means you can say for sure that there is a growth. Okay, it will be around one number. It looks like stationary. So that means instead of directly forecasting the height after 1 month, what we can do is we can turn to this one. Okay, we'll turn to this one, the increments. We'll try to see the increments here. Instead of seeing the whole height, we'll see the increment from time to time. Okay, this is the differential process, you can say. After applying differencing, we see the increase in heights. This is one increment, this is one increment, this is one increment, and we'll try to forecast the increment. Though our answer will not be the increment, our predicted value will be the total value, but first we'll find this one, then we'll add this value to this value, whatever the last value we must have here, that value. Okay, suppose it's 180. Okay, then we'll predict 180 plus the increment value, whatever is, suppose this is 5.3. okay, you add this one, because this is what you can predict using a time series ARIMA process. You can predict this, then you can add to the present height. Okay, so 180 plus 5.3, that will be our answer. However, there is one assumption. Again, we assumed here that although the process is not stationary, there is an add-on effect from time to time. The differentiated process, after applying differencing, okay, if this becomes stationary, I'm not saying this will become stationary, because the growing, if you see from time to time, that might also be growing. Suppose someone is traveling, okay, someone is accelerating. If you see the growth from time to time, it might decrease. There might be a growth. You must have seen in cricket matches also. The score will increase, but it will increase at a decreasing rate. There we need double differentiation. If the growth is at a normal in T20 matches, you see the scores are increasing at increasing rate. Okay. So here if the increment still increasing, then what? Then we can apply a time series model here. Okay. So suppose you get data like this: 5, here 6, here 7, here 8.2, that way, then this is still not stationary. Okay, so we'll not be satisfied with this one. We'll do once again. Okay, so this is first differentiation. Now we deleted this one. You have to differentiate once again. Okay, if you do that, 1.2, you will get this way. You should get 0.9 here, suppose. So this way, if the numbers are around 1, you can apply any selected ARIMA one. You need to decide here, and then you can predict this one. From this one you have to go back to this one, because you want to predict this one. Suppose you get the data, and for some party you want to predict this value. You will not say all the background process, right? You have to say this one. So how to go from here to here? That is called inverse transform. First you need to transform your data, then you have to apply inverse transform to go back and to predict the final one. Like in this case, the final value is this one. Okay, what is inverse transform here? We predicted this one, and before predicting the height at this point, you have to add this one. It's a simple thing, okay, though, but this is called inverse transform here. So you have to transform the data, you have to make it stationary. After transforming the data, you apply your ARIMA model. If it's from ARIMA, we'll see. Then if you see some other kind of behavior like seasonal behavior or maybe any such other behavior, we'll deal those things separately. What I'm saying here is, if this is stationary, if this is ARIMA, that means there is an integrated effect. Integrated means add-on effect from time to time. Then you need to take those add-on effect, take out those add-on effect. Okay, you need to difference time series time and again to make it stationary. Okay, so the original series is ARIMA PDQ. Now let's do one example. Okay, not example. Now let me write the general representation. How you would represent one ARIMA. You know ARIMA, how we write? ARIMA PQ. Let me write the representation of ARIMA PQ. ARIMA PQ. If you remember last time, we wrote this way: phi b, any function of b, xt minus mu. This is a polynomial, okay? Xt minus mu is equal to another polynomial, theta b et. This is ARIMA. Now if you go to ARIMA, suppose this will be a function of b, okay, whatever. If you want, I will write the full function here, 1 minus alpha 1 b. Normally we get this way. You continue, then you write alpha 1 alpha to alpha p, right? And this is our polynomial here, and xt minus mu I will write here the same thing, okay, xt minus mu. So we need another one in ARIMA. We need another one in ARIMA, pdq, okay, pdq. So this is there, and for this one, this d, we'll write one factor here, okay, before xt minus mu. 1 minus b. If you write 1 minus b, you need to differentiate once, okay. So 1 minus b square, 1 minus b power d. This factor you have to find it out. Then this will remain the same, xt minus mu. That means if you want to compare this one and this one, you see this one is changed, okay. This function of b is equal to this, okay. This function of b is equal to, this function of b is equal to this. That means you have to drag out the factor 1 minus b power d, where you have the add-on effect, that you have to separate. This side will not change, but yeah, sometimes it will also play crucial factor in ARIMA classification. We'll see that. So let me write this way, 1 minus b power d, then I have to write xt minus mu, then I have to write theta b et. Okay, theta b also, if you want, I can write the polynomial here. If you remember, we write beta here, beta 1 b up to q, we write beta q b q. If you remember, et, this way. This is the complete ARIMA pdq, okay. This is the question, okay. Now we have two methods. We'll find the solution using two methods. So let me do it by method 1. You find all the 1 minus b factor here. How can you do that? You bring everything to the left hand side, 0.6 xt minus 1 plus, sorry, this is minus 0.3 xt minus 2 minus 0.1 xt minus 3, and keep these here, et minus 0.25 et minus 1, this way. Now this one will not make anything, you know, we can write in the form of a polynomial. In the left hand side, you write using b, xt minus bxt, that is xt minus 1, okay. So if I take xt common here, I will get 1 minus 0.6 here, b. I have taken xt common from here, minus 0.3 b square xt. So b square here, minus 0.1 b power 3, and in total xt, that's all. B power 3 xt is xt minus 3, b power 2 xt is xt minus 2, that way. And here also we'll write et minus 0.25 b et, and finally if you see, it will take that form, the general form. But we need to find the 1 minus b factor if any is. For that, if you want, you can check this way also, 1 minus b you write, okay. Then you see anything you need to change. I have to write plus 0.4 b, so that this will be compensated, minus 0.4 b square. So if you take 0.4 b, you will get again 1 minus b, but we have minus 0.3, so 0.1 b square you have to write minus 0.1 b power 3 xt. Okay, you will get this way, then it will be 1 minus 0.25 b et. Now if you see, there is a 1 minus b common from the first two terms, then the next two terms, then the next two terms. If you take 1 minus b common, you will get 1 here and plus 0.4 b here, then plus 0.1 b square here. That means if you are unable to find 1 minus b factor, okay, then make it sure that there is no I effect. It's ARIMA, it's not ARIMA. 1 minus 0.25 b et. You check for this polynomial as well. If there is a 1 minus b factor, 1 minus b factor, how can you check? You put 1 here in b and you check whether this expression is 0 or not. If you put 1 here, 1 plus 0.4 plus 0.1, that is not 0. So 1 is not a root of this polynomial. So definitely will not get 1 minus b factor. Here if you put b1, you check it will be 0. Okay, this is 0 for b1. So we thought that 1 is a root and we wanted to extract that 1 minus b. This is the best way you can extract 1 minus b. You write 1 minus b, then you go on adjusting term by term, you will get that way. Okay, it's quite easy. So now that this is 1, that means we are sure the original, the ARIMA equation that was given, that was non-stationary because you have 1 minus b factor. However, there is no 1 minus b factor in the second polynomial. So this is fixed now 1. Okay, and you see the degree of this polynomial too. Then we'll write this way. This is ARIMA, this is 2, okay, and this is 1. D we write here, this power is d, and this polynomial power 1. This is ARIMA 2 1 1. That means you know that if you apply differencing, then it will turn to a ARIMA 2 1 stationary series. Okay, that's for sure because there is no 1 minus b factor here. We'll do by another method. Let's go to method 2. In method 2, we'll apply the old ways. In method 2, okay, better I will erase everything. It will be easier for me to do once again. We'll change our track from here. So this is the series. In method 2, we'll try to apply directly differencing method. Okay, so we'll write this way. Even we don't need this one, right? We don't go to b directly in method 2. So we'll change it to method 2. In method 2, you apply here xt minus 0.t xt minus 1. You write xt minus xt minus 1. Those similar way we are doing, but you will see the difference. Xt minus xt minus 2, you have to write xt minus 1. Then you have to compensate, and I think you will get 0.4 xt minus 1, that is present here anyway. So if you see 0.4 minus 1, that is 0.06, and we want here xt minus 2 anyway. If this way you are not able to do, then that's fine. Okay, we'll not do, we'll check 0.2 xt minus 1 minus xt minus 2. I have 0.4 xt minus 2, but I have minus 0.3. So I have to write minus 0.1 xt minus 2. So you check, yes, we have minus 0.1 xt minus 3. That's fine. Minus xt minus 3. So if I write a minus here, I should get plus 1. Okay. So plus 0.1 here. No, I have minus 1. So I have to write plus here. So I want to write minus anyway. So I have to make it plus. So then this will be fine. So plus 0.1 xt minus 2. Here plus minus 0.4 plus 1 minus 0.3. Okay, that's fine. And the right hand side will remain the same. Et minus 2.5 et minus 1. Then we'll take xt minus 1. Okay, this one will write yt, or maybe you can write delta xt plus 0.4 delta xt minus 1 plus 0.1 delta xt minus 2. Okay, that is equal to et minus 0.25 et minus 1. Then what will happen? Then if you see, if you consider this one, this time series, if you are not compatible with delta xt, you can term is yt, another time series. Okay, just change the notation. Yt minus 1 plus 0.1 yt minus 2 is equal to et minus 0.2 et minus 1. Okay, if you predict here the value of yt plus 1, from y you can go to x later. We'll see that. But what is the values of, what are the values of p dq? These are we are finding here. Okay, so if you check here, we can do it any more. We'll go to the next example where you have to do twice, I suppose. But here we don't have any such xt minus 1 here more. I mean, you can write yt minus 1. You can try once, you will see. But instead of doing that way, what you can do is you find the characteristics polynomial. Okay, that is 1 plus 0.4b, we write z. Okay, plus 0.1 z square. Then check this way. Even before applying this method, you could have checked here as well. That is the normal procedure. In method 2, you find the characteristics polynomial here, check for the roots. Okay, check for the roots. You will get 1 minus 0.6 z minus 0.3 z square minus 0.1 z power 3 is equal to 0. You check the roots. Okay, if you get a root 1, you will get for sure, in this example we know you will get a root 1. Then this is not stationary, right? Because you have a root 1 that you want to discard, actually, how can you do that? You have to apply this method, 1 and 2 other roots. This is a cubic one. You can find all this. Now if you go here, if you try to find the roots here, you will get 1 plus 4 z, you can make it 10. Okay, plus z square divided by 10 here, that will come here anyway, and that is equal to 0. So if you find here minus b plus or minus square root b square minus 4ac, see, I didn't check here because I have done this problem by other method. Okay, so you have to check here. If you are using by method 2, you have to check here before applying differentiation. Okay, before differentiating you have to do that 2a. Okay, so this is 20. So these are the roots. A is minus 2 plus square root of 6i, b is minus 2 minus square root of 6i, So if you find this one, this will be minus 2 square plus root 6 square, that is 6, this square root of 10. Okay, here also b mod you will get the same, square root of 10. They are greater than 1 in magnitude. So this is stationary. Okay, this one is stationary, the differentiated one is stationary. So we will not differentiate further and we will stop here and we will pick up the AR and MA, whatever it is. Suppose the degree is 2 here. Okay, 2 and here 1. So this is stationary anyway. And finally we'll classify this one as ARIMA. You need to remember how many times you differentiated once, that will be the mid one. This is D, and these two 2 1 here, so 2 1 will write. So this is your classification by method 2. Now we will do the next problem, that's very important. Go to this problem. Yeah, there might be a problem here. It will take another 5 minutes. Okay, not more than that. So let me bring everything to the left hand side. 2xt minus 7xt minus 1 plus 9xt minus 2 minus 5xt minus 3 plus xt minus 4 is equal to et minus 2. See the possible mistake what we can do here. You write this way, 2xt minus 2xt minus 1, that's fine. So this will be 2xt minus xt minus 1. Again I am assuming that this is not stationary. Okay, you can check the characteristics polynomial for that, because this is a problem anyway. I accepted this is ARIMA. I am only finding PDQ. So you have to start checking from here in method 1. So I have written already 2, so I'll write 5xt minus 1 and I need another 5 here, plus 5xt minus 2. Then I will take common minus 5. I'll get xt minus 1 minus xt minus 2. Okay, how we write? Nebula xt, right? Here in time series. So 2 nebula xt minus 5 nebula xt minus 1 plus 4 nebula xt minus 2 minus nebula xt minus 3. Okay, that will be et minus 2. Now if you check this one, okay, you can take yt as well. Let me write characteristics polynomial at least here. That will be 2 minus 5z plus 4z square minus z power 3 will be 0, and we'll check only for 1. When you are checking for ARIMA, remember you have to check only for 1. So if you put 1 here, 2 minus 5 minus 3 minus 3 minus 1 minus 4 plus 4 0, still there is a 1 here. Okay, so if there is a root 1 here, this is not stationary. You need not find all. You are sure that this is not stationary. There is a 1 root here. You try to extract that one from here. So I'll write 2 nebula xt minus 2 nebula xt minus 1 minus 3 nebula xt minus 2. Okay, that is minus 5, and I need plus 3 nebula xt minus 2. So I will have one more nebula xt minus 2 minus nebula xt minus 3. So here nebula xt minus 2, that is et minus 2. Then in the next step, if you see, you take this one 2 common, nebula xt minus nebula xt minus 1, that will be nebula square xt, and the second one is 3. Okay, if you take 3 common, nebula xt minus 2 minus nebula xt minus 3, xt minus 2 minus xt minus 3, what I have written, minus 2 xt minus 2, then minus 3 I have taken common, right? So you should get yeah, I compensated this one. Then I had to write plus 3 xt minus 2 . The first two terms are here, okay? So then this one, this is over. Part of this is over. So what I have done is minus 2 nebula xt minus 1 I have written. So I had 3 xt minus 1 here, right? Okay. To write xt minus 1 here, 2 here, then let me write here minus 3 common. This is nebula square xt minus 1. Then go here, we have nebula square plus nebula square xt minus 2, okay, is equal to et. There will be no confusion if you write one by one term, because when you are thinking everything there might be a problem. Now see what is the problem here. If you find the characteristics polynomial, you can take this as yt also, that will not create a problem. You can take this one as zt, okay. In any case, if you find the characteristics polynomial here, you get 2z minus 3z square plus z power 3, okay. 2 here, this is 2 minus 3z here plus z square. Now if you check this one, and if you try to find the roots, you put 1 here, 1 plus 1, okay, 2 minus 3, 3 minus 3, 0, again we have 1. So what will happen? So again you need to differentiate this one. Then if you apply the same procedure, you will go to the next step, okay. Then what will happen? Here you write 2 nebula square xt minus 2 nebula, okay, let me change it, otherwise it might create similar problem. So I'll change it to zt, okay. So this is my new one, minus 3 zt minus 1, sorry, minus 3. So nebula square xt I have taken zt, remember zt I have taken nebula square xt. Normally I start taking from here yt anyway. So this is zt minus 1 plus zt minus 2, that is et minus et minus 2. So this one also will try to factorize, okay. So what will happen? We'll cancel here. It will take 2 minutes more, okay. So next what will happen? Let's create space here. Now 2 zt minus 2 zt minus 1 minus zt minus 1, okay, minus 3 z3 minus 1, and then we want plus zt minus 2 is equal to et minus et minus 2. So if you take this common, okay, 2 zt minus zt minus 1. So if you take 2 common here, you will get nebula zt, okay, minus 1 common, nebula zt minus 1, and this one you can write ut, 2 ut minus ut minus 1. There is no more factor, okay, 1 minus z factor here, and that is equal to et minus 1, et minus 1. So if you see the power here, power is 1, right? The power is 1 here, power is 1 here. So how many times we differentiated? If zt is square, so 3 times we have differentiated, okay, and here ARIMA 1 1. So you will classify this as ARIMA. How many times differentiated? 3 times. Not this one. This one is ARIMA 1 1. This one is ARIMA 1 1. I am not talking about this. I am talking about the original series. This series, okay. This one will be ARIMA 1 1, and 3 times we differentiated this way. But this is wrong. This is wrong. That is what you need to recognize here. You should not go to the last one. You have to cancel all these, okay. You have to stop here. These are wrong. Why these are wrong, I'll tell you. This classification is wrong. What you need to do is, before going to the next step, okay, before going to the next step, you have to check it like this one. From here we'll do once again, okay. We have this. From here, when you write this is, we started from here, right? So we wanted that one, okay. Let me go there. Yes. Yeah, up to this it's fine. So up to the last step it's fine. So before going to the next step, up to this it's fine. Now before going to the next step, or what you can do is, from the starting point, I will go there. If you check this polynomial, okay, and this one here, there is a common, okay. If I write this as 1 minus et minus 2, this is b square et minus 2. So there is a common 1 minus b here. You need to cancel this one before going to the next stage, okay. So if you write this way, if you take 1 minus b common here, whatever we got here, maybe 2zt minus, so if you write using b this one, okay, so that 1 minus b factor you need to cancel, okay. I think you will get 2zt minus zt minus 1 xt, you will get this way, zt you will get this way, 2b, let me write 2b minus b minus 1, 2b minus b minus 1 zt. This series you have to write this way, because if you multiply these two, you will check that you are getting this 2zt here, okay, then 1 minus 2b minus b 2 minus b, 2 minus b. We'll check this one, not a problem, 2 minus b. Now if you multiply these two, you will get 2 here, then minus 2b minus 2 minus b, then minus 2b, this is minus b, and plus b square. See, this is what we got, right? B square minus 3b plus 2 zt. This is what we have, b square zt, that is zt minus 2. 2 zt is here, okay, minus 3b zt. 3b zt means 3 zt minus 1. So this term is equal to this term, that is equal to this term. Now we have to cancel this one. So if there is any common factor, you need to cancel. So then what will happen? Our series will be this only. 1 minus b is no more here. Okay, this is no more there. Now here also, when you cancel 1 minus b, you will have this one. So finally your series is 2zt, okay, minus bzt means zt minus 1, that will be et plus et minus 1, this one, okay. And remember, zt is delta square bt, so it's actually ARIMA. How many times we differentiated? 2 times, not 3 times. See, it's not 3 times, this is wrong, okay. You have to write 2 here, 2. Then here if you see zt minus 1, 2 minus b, here we have 1, and here also we have 1. We got ARIMA 1 to 1. This is correct. 1 to 1. This is correct. Okay. This is not correct because you have to cancel out the common factor. Okay. If there is a common factor, you need to cancel out. So I cancelled here. What you can do is, when you start the problem, here only you have to check. When you write the characteristics polynomial, if there is anything in common, I mean from the right hand side, that you need to cancel. Even I can make a simpler example to before ending the class. See, if I write something like this, this is the example, classify ARIMA PDQ. So if you consider this example, I will write the characteristics polynomial, and it will be 2 minus z here minus z square, that is equal to 0, then z square plus z minus 2, 0. So if you find this one, then minus b plus or minus square root b square minus 4ac, that is plus 8 divided by 2, 3, minus 1 plus 3 divided by 2, minus 1 minus 3 divided by 2. Okay. So this is 1, and this is minus 4 by 2, minus 2, 1 minus 2. Okay, these are the roots. So 1 is here. So seeing 1, you will say that this is not stationary. Okay, then you try to apply, you differentiate. Okay, then you come back to, I'll write this way, 2xt minus 2xt minus 1. I have minus xt minus 1, then minus xt minus 1 I will write, then xt minus 2. Okay, then I will do this way. This is the common method. Okay, but the problem here is it's not correct. That's what I want to say. So what will happen if you take if you change it to yt, where yt is xt minus 1 and minus 2 yt minus 1 is equal to et minus 1. Okay, this is ARIMA, this is ARIMA. Okay, this is ARIMA 1 1. Then what about this? I have to write it as 2, sorry. This is ARIMA 1 2, this is ARIMA 1 2. Then you will classify this as ARIMA 1 1 2, but this is wrong. That is what I am saying, because before going further, if there is a root that is common here, okay, you have to take that. That means this one also, right hand side also you write. So what you need to do is, you got one root, that's fine, but this is not ARIMA. This is not ARIMA. What you need to do is, before going further, that way method 1 is better. Okay, before going further, you try to factorize this one. If you try to factorize this one, we got this factor, right? So you write this way, 2bxt 2 minus bxt minus b square xt. You write this way. Then this one you write 1 minus, even if you have 1, it doesn't matter. You have a 1 minus b factor, right? But I wanted to have something, so 1, this is 1 minus b square et, okay? 1 minus b square et. See, 1 et b square et minus 2. So we have a factor 1 minus b here, we have a factor 1 minus b here. We got the roots, right? 1 minus b something here. So what will happen is, this 1 minus b factor here, you have to cancel it before proceeding further. So if you cancel it here, here only it becomes stationary. You need not go beyond. Okay, I will show you that. So this classification you need to remember. Yeah, all right then.
Okay. Thank you, sir.
Okay, fine.